Okay, so let us get into the second lecture on I/O. I will be going through storage media, this time solid state drives. The first lecture we covered hard disk drives. So more recently and over the past 20 years, solid state drives have been increasingly come in use. What I will deal with or talk through today is what's the basics of these. I'll get down to transistor level. It was exciting for me to actually get down to that and then come back out to the solid state drives. And the reason is because there are very peculiar characteristics of solid state drives with the write, program, erase cycles, endurance, where it is interesting to just know a little bit more into details about what's going on underneath these drives. So the basic building block of a solid state drive will start with the transistors is a MOSFET transistor. In fact, a MOSFET transistor is now the basic building block of a lot of semiconductor circuits, processors, volatile memory, non-volatile memory, all of it. The MOSFET transistor stands for metal oxide semiconductor field effect transistor. Essentially, you have a source and a drain and a gate that acts as a control point in between. You can apply an electric field across source and gate through a voltage. Say in this case, source is on ground, the drain is at VDD. By default, there will be no current flow because between the two N plus areas, there is a P substrate. By applying a voltage at the gate that is beyond a certain minimum threshold, you are able to then build a conducting channel that does now allow the flow of current. So the transistor acts like a switch that can be turned on and off by applying a voltage at the gate above the threshold level. So let us now see how this kind of a transistor is used to build memory components and flash drive components. And I'll start with a simpler example on DRAM and then go to the flash devices. So DRAM memory is dynamic random access memory, and it uses the MOSFET transistor as its basic transistor. But there is no charge being stored, and at the end of the day, if you want memory to retain a value. So the way the retention of value is done with the transistor is by adding a capacitor at the end of the source. So now you are able to charge the capacitor, and if the capacitor is charged, you can call it a 1, and if the capacitor is discharged, you can call it a 0. So how do you charge a capacitor or bring it to state 1? You charge the drain side to the supply voltage at VDD. Then you switch on the transistor by applying a gate voltage above the threshold voltage that opens the circuit from drain to source. Now that the circuit is open, the charge will flow and charge the source MOS capacitor. So now you have a 1. You can now switch off the gate and the charge is going to stay there. Now to read back, which is the interesting part of the memory, is you want to store but you want to read it back. You set the drain to 0 volts now, and you again switch on the MOS transistor by applying a gate voltage that is greater than the threshold voltage. And now if you detect a current flow, you can assume that that current flow at the drain came because the source had charge stored in its capacitor. So it must have been a 1. But if there is no current flow, then you can assume that there is no charge stored. So it is a value 0. And the current flow is read at the drain side by sense amplifiers that sense whether the current is flowing or not. The caveat here is that the charge that is stored at the source capacitor is so small that it is just lost with the read. So whenever you read, you have to charge it back. The other thing is that even without reading, the charge in the source capacitor is lost, just periodically due to leakage. So the solution for that is that in DRAMs, constantly you need to replenish this charge about every 64 milliseconds or less in time. And that's how they work. And that is the reason they're called volatile memory, because the moment the power is gone, the ability to replenish the charge will be gone, and so the charge will be lost. This comes in the category of volatile memory. You can certainly use it for memory, but you cannot use it for persistent storage. So in solid state devices, how do you then build non-volatile memory, which is persistent in nature? The same principles are applied, but this time there is another technology in between where you can put a floating gate between the gate and the P substrate. So if you insert a floating gate here, a floating gate essentially has the ability to store electron charge, and it can store it without any active power. You just have to pull the electrons in there. So once in this state, if you do not have any charge pulled into the floating gate, the device will act as a normal MOSFET transistor. So there's no charge in the floating gate, it just acts normally. You apply a voltage at the gate that is greater than the threshold voltage, and it will allow current flow between the source and the drain. But now if the floating gate is charged with electrons, it is not enough to supply a voltage at the gate that is just above this threshold voltage. It in effect increases the amount of threshold voltage you have to apply to cause that same charge to flow. And that property, that now you have to apply a greater voltage to allow this conducting layer to come between source and drain, is used in identifying whether the floating gate is charged or not, or whether it is a 0 or 1. So now when the floating gate is charged, you can assume that it is 0, and when the floating gate is not charged, you assume that it is a 1. So how do you read data out of it? Well, apply a source voltage 0 and a drain voltage of VDD. So you have an electric field here. And you apply a gate voltage that is greater than the first threshold, but still less than the second threshold of opening up the gate if the floating gate were charged. So now we're dealing with two thresholds, TH1 and TH2. If current now flows between the drain and the source, then you can assume that the floating gate is not charged and the MOS transistor is behaving normally. But otherwise, if the current is not flowing, that means the floating gate must have been charged. And then you can assume it's a value 0. So that is the basic model of storing charge and then inferring whether it is a 0 or a 1. So that's the reading, but how do you move charge into the floating gate? There are field emission principles used here, and hot electron injection is one of those. You basically create a conducting channel here between the source and the drain using normal techniques. You apply an electric field, put voltage VDD at the drain, and get the source to be 0 volts, and then apply a high voltage at the gate. And when the electrons are flowing and a high voltage is applied at the gate high enough, the electrons are going to move from the conducting channel up into the floating gate. And they move there, and then you can preserve them there. So that is how you can charge a floating gate through the use of a special high level of voltage and using the process of hot electron injection. The opposite of that is roughly used for erasing the floating gate charge. You can apply a high negative voltage at the gate to push the charge out, or otherwise you can apply a 0 voltage at the gate and then apply a high voltage on the lower part, the source, drain, and P substrate, and that will pull the electrons down out of the floating gate. But either way, this is a process that moves the electrons out of the floating gate and makes it again behave like a regular MOS transistor without any charge in the floating gate. So these are two ways you can write and erase the charge. So floating gate transistor effectively without charge represents a bit value of 1. A floating gate transistor that is charged represents a 0. And now, one more property to keep in mind is that there is a certain level of degradation that happens over the lifetime of write and erase cycles. And because of that, a floating gate charge can only be reliably read or written up to a certain number of cycles. And then you can't use that anymore because of charge leakage, or because the material that you have is not able to reliably store that level of charge. Now, without erased cycles, you can store the charge in the floating gate for over 10 years, 10 years, 20 years. It's a long enough time frame. But only the number of program and erase cycles are limited. So that is a caveat that comes with these devices. So now we get from a floating gate MOS transistor to how it is used in a flash storage. The first building block for that is a NAND flash string. And instead of just having a source and drain and every transistor have its own contacts, they are actually put in a serial string, a bunch of these, between 32 and 128 cells in a string. And there is only one source line at the beginning and one bit line at the end. It is done this way because you get space efficiency this way. These are called strings. When you connect more of these transistors together in series, the current drops because each of these transistors act as resistances. So what it does also is it does slow down the read path for values here. And keep in mind that just because they are in a string doesn't mean that you just have to read or write all of them together. But only one cell in a string can be read or written at a time. And just because you will sense at the end at the bit line is a cell on or off, and you can only determine that by looking at one cell. You could not, if you were trying to get two cells, that are on, there's no way for you to find out which one it was. So the way it works then is you basically apply a read voltage to the word line, and each of these cells is connected to a word line. And for every other word line that you do not want to read, you just put a pass voltage. And a pass voltage means it's higher than the second threshold, so the current will, of course, flow through those. And then you select the source line and the bit line voltages to select this string. And the string is selected, and one of the word lines is kept at the read value. The other ones are kept at the pass value, so the whole current will flow. And you still now are able to measure just based on the word line that you wanted to detect for a value that's either 0 or 1. And so a voltage drop at the bit line, will indicate that a discharge is happening through current flow. So if a discharge is happening, current must be flowing, so no charge at the floating gate, bit value is 1. But if there is no discharge happening on the bit line, then obviously there was no current flowing, which means that that's due to the charged floating gate, so the bit value is 0. So now you use a concept of a series string where you're able to read the cell that is connected to one of these word lines. The flash then is built more in the shape of a block. You don't want to just read one of these bits at a time. You want to read multiple bits. So word lines are connected to multiple bit lines together, like word line 0 will be connected to several bit lines. And this connection from each of these word lines going into many of the bit lines forms the page. So in this case, you got 16K bits, and they're all connected through the same word line and through every word line, and each one is a page. So this one has 64 word lines, and each of these word lines is a page. Now, because each page has 16,384 bits, each page has 16K bits, or Each page has 2 kilobytes per page. So this whole block together, because it has 64 pages and 2 kilobytes per page, forms a 128 kilobytes block. So a block is essentially built from an array of many flash strings, and they are all connected down through the word line. Each one of these word line connections is a page. Data is read and written a page at a time. So the minimum writing will be at 2 kilobytes in this case. Erase, however, in a block cannot be done a page at a time. Erase is done at a block at a time. So the whole block of 128 kilobytes here will have to be erased together. And that is because of how materially this whole thing is connected or created, and how you have to get the high voltage down to the substrate level that the whole block will get erased. So these are some of the nuances of using this technology. How is a flash memory die now created? Here's an example of a Samsung one that I took. And this is a die which has 4 planes and 2 gigabit per plane. Internally, it puts the blocks together in different planes, and the difference between blocks and planes is a plane has several blocks, and the reason planes come in is because a flash die is able to do some simultaneous operations at a plane level. So with each plane, it can have its own registers and store data and input and output data. So it allows for some parallel operation. Otherwise, the operation at a single plane level is... So each plane has, in this case, 2048 blocks. Now we know each block is 128 kilobytes. I just took a specification that this flash had taken. Each of the 128 kilobyte blocks is again 64 pages, 2 kilobyte per page. Each of the page then has 16,384 cells, and you store one bit per cell. The flash memory, in addition to just storing these cells, also has logic to get the row and column address decoding done. You need high voltage to erase and write, so it has a high voltage generator, has a controller to manage the input and output, and registers to store data. So the minimum write is at a page level, which is 2 kilobytes. The ability to write is only possible after a page has been erased. That is interesting because you have to assume certain things. Because you're only able to write a 0, you have to make sure that everything is 1 again, which means the charge is erased, and then you start writing your zeros. So new writes are possible only after a page is fully erased. And the minimum erase unit is a block which is 64 pages, which is 128 kilobytes. This particular flash die has the random read of 20 microseconds, serial access of 25 nanoseconds here. It has a page program time of 200 microseconds, so the time it takes to program a page is more than it takes to read a page or write a page. The block erase time is 1.5 milliseconds, so that one is actually the higher one. The endurance in this case is 100,000 write erase cycles or program erase cycles, and they guarantee a data retention of 10 years, so it'll be there for more than 10 years. This is from 2005. There have been other advances in this technology where you would read off 3D NAND. In a 2D NAND, the cells were all put on a horizontal area, and the higher cell density that was coming up was happening because of the shrinking cell size. But that also reached its limits in reduction. So with some new technologies and new methodologies in processing semiconductors, the 3D stacks came up, which was really to layer these cells vertically up. And the NAND string now is built vertically instead of just horizontally. That allows the wafer to grow up and vertically, and you achieve more density because you just get the third dimension to be used now. 64, 96, 128, and these layers have been coming up close to 176 layers now that are available now, and that's where the state of the technology is at this point. The other way that cells have been made more dense is by having the ability to put more bits per cell. And the original cells were single level cells. They had the ability to produce 1 bit per cell, which means you just had 2 voltage levels that had to do that, 0 or 1. The other cells that came after that was the ability to store 2 bits per cell, known as MLC. Although it was called multi-level cell, now there are even more multi-levels than MLC. So going back to how things were structured, MLC means 2. At times it may refer to more, but there are other terms for those. For 2 cells, for 2 bits to be stored in a cell, you need 4 voltage levels to be read. So you need to read back 4 discrete voltage levels. It is not enough to have the threshold 1 and threshold 2. You will need more thresholds in between now to understand what is actually stored. And in the triple level cell, you have 3 bits per cell. You need 8 voltage levels, 2 to the power of 3. Quad level cells, you have the ability to store 4 bits, but it comes at the cost of storing 16 voltage levels. Now, each of these voltage levels and threshold variances happen because you save a different level of charge in the floating gate. And then when you sense the voltages, or you set a voltage, you then still go through the same principle of, is a current flowing or not upon applying a certain voltage? And you just have to get more precise with the amount of charge that you are able to program into the floating gate. The endurance numbers for these are different. It's interesting because at the SLC level, you could program erase 100,000 times. And by the time you are getting to the QLC level, that program erase cycle is less than 1,000. And the reason this is happening is we do know that write-in erase is harmful, but as you try to be more precise with the charge, the ability to have precise levels of charge stored through this process degrades much faster. So another alternate unit that is terabytes written, and terabytes written is pretty much a calculation based on the total capacity of the drive and multiply that by the program erase cycles and you get terabytes written. So if you had 1,000 program erase cycles and you had a capacity of 0.1 terabytes, like 100 gigabyte flash, the terabytes written will be 0.1 times 1,000, which is 100 terabytes written. The prominent reason I think these alternate units have come in place is because with higher dense storage and capacity, the program erase cycles were going down. So instead of having a bad metric, the other metrics seemed like nicer. Like it's nicer to say 1,000 terabytes written than to say, oh, I only have 1,000 program erase cycles. Flash dies are put together in the building of a solid state drive. It is one of the most important components that actually stores the data. The advantage of having now solid state drives is you don't have any moving parts. There is, however, the need to be much smarter about how to manage this. Unlike hard disk drives, which were simpler to manage, now you need more intelligence. You need to of course, manage the multiple NAND flashes you have here, but you have to worry about wear leveling. Wear leveling really means that instead of just taking one block, just erasing and programming it, and then going to hit the endurance of that one block and making it useless, you really try to distribute it across and keep all the wear that is happening on the flashes even. Then you also have to do a logical block address to a physical block address mapping. Physical address is really for this drive to determine what is the best place to store data. But still it has to interface out and give an addressing scheme. So the external users or systems don't have to worry about it. So it does keep the logical block address to physical block address mapping. You have to still, as you build a drive, manage the host interfaces to it. And the interfaces are SATA, SAS, NVMe, depending on which kind of SSD you are creating here. You also have to manage garbage collection. And what drives do is, instead of, we know that the erase time is high. So instead of doing the erase time synchronously while a write request has come, you just manage erases offline and make blocks open to writing for workload, so writes go faster. And that process is called garbage collection. Solid state drives also keep some extra provision capacity. It keeps performance going. It can manage against bad blocks that you have that you cannot use anymore, or that were already created like that as bad blocks. There is some extra provision capacity kept in drives, and the enterprise class solid state drives will keep more provision capacity around. The non-enterprise ones will keep less capacity around, but still some capacity is kept for this kind of wear and performance improvement. And to do all this, there is a controller, and it also uses effectively an SDRAM to keep temporary memory. And as it is queuing up all these requests, getting all the responses back and serving back responses through the interface, so it uses the SDRAM buffer over there. Interesting differences also come from NVMe versus SAS or SATA. So here's where I have taken an example of a couple of drives. One is a Samsung and another one is a Micron one. Both were at 2 terabytes, and they had one was with NVMe versus the other one was with the SATA interface. The NVMe is the faster one, and I'll cover it a little more in the next lecture. The SATA interfaces are more from the whole backward compatibility, because that's how systems have been built to interface with drives. So the SSD on the Samsung, on the SATA interface, does 560 megabytes a second read, roughly that at the write level as well. The capacity is at 2 terabytes. The Samsung one has a 4 gigabyte DRAM cache and 2.5 inch form factor for a disk drive. Now, technically, 2.5 inches was a hard disk specification. It is technically meaningless for flash SSDs, but because the current enclosures are available like that, and the big adoption of SSDs happened because they were able to fit nicely into those systems with the SATA interfaces as well as with the enclosures, it still has a 2.5 inch form factor. And the interface is SATA, which is standard. It gives you 6 gigabits per second. These drives do way better on random read, and they will advertise their numbers. It doesn't technically matter a whole lot between random or sequential, because there is no platter that's running around. These are all independent blocks in independent locations. So these are close to 100,000 levels for the read and write on this SSD. The endurance on this one is 720 terabytes written. Now, 720 terabytes written on a 2 terabyte drive means if you divide 720 by 2, it's roughly 360 write erase cycles. Now, that is low, and it is low also because this is a QLC technology, as in the type. So it keeps 4 bits of information per cell, and we just sort of went through. The more levels you keep per cell, the worse the endurance gets. So it only keeps, although they don't put it out there in their numbers, 720 terabytes written on a 2 terabyte drive really means you got 360 write erase cycles for every cell. And the other good thing about this drive is the active and idle power consumption. The idle power really goes low, and the active power is also low compared to the hard disk drives. The NVMe one, interface one, on the other hand, has a much higher sequential read and write capability, and it has got nothing to do with the flash technology. It has all to do with the interface that it has to send and receive data, with the NVMe versus the SATA one. It is as well a 2 terabyte drive. The Micron one has advertised 96 layers, 3D technology, triple level cell NAND. I couldn't find the cache, they didn't write about it. But it does also come in a form factor which is an M.2, goes into a much smaller area. Now that you don't care about the SATA interface, you also don't care about the 2.5 inch enclosure. So the NVMe drives are coming in different form factors. The random reads and random writes are approaching 500,000, and that's just huge. You are able to use much of the capacity, and now you're able to get to use the high random or the low read and write times of the flash storage underneath. The endurance is 1200 terabytes written. Now 1200 is more than the 720. Yeah, so you divide this by 2, you get 600 write erase cycles, and that's better than the QLC one, possibly, because it's a triple level cell, so it has got almost double endurance compared to the Samsung one. And it's again got a low idle power requirement as well. So that was on the SSD drives. They're generally better than hard disk drives because lower power, much faster to read data out of these, faster to write data into these, no problems with getting to seek times, access times. They do have one problem though, and that is that they do have endurance limits. They can only be written so many times. We did not have those limits with the hard disk drives. And so that's the give and take. They're also costlier, but the cost has been coming down only, so that's becoming a lesser of an issue lately. So the next lecture will be on the storage interconnect protocols. This is where we go a little bit more into SATA, SAS, NVMe, and also on the SAN and NAS storage out there that is over the network. Okay, thank you then.